Hi, this is Dr. Hay. Let's do a problem involving total internal reflection. This is a problem called View from Underwater. All right, while swimming underwater in a pool, you look up and notice that you see objects above the surface in a circle of radius approximately 2 meters, and the rest of your vision is the color of the side of the pool. The question is, how deep are you? Okay, so here's you down here. You're swimming underwater and you're looking up at the surface. First, let's just talk about how this could even happen. Okay, so consider light rays coming in from the outside to your vision. And the trick is you have to trace the light rays back to where you think they are coming from. And what is making this happen is total internal reflection. Let me show you what I mean. So you're down at the eye down here looking upwards, and you see everything in a circle of approximately radius 2 meters. Okay, there's your circle. And when you look up, you see this cone. You see this cone of vision that looks like the outside world. And everything else outside of it, out on the right and on the left, looks like, and actually three-dimensionally, looks like the side of the pool, the color of the side of the pool. Okay, so let's follow a couple light rays here. I'm going to trace one of these gray light rays. Okay, so here's like a light ray coming from a tree out here. All right, so it bends toward the medium with higher index of refraction, and it comes to your eye. Now to you, let's trace that back. It looks like this light ray is coming from here, right? Even though it originated from over here. Okay, let's trace back another one. This one is from a tree that's a little bit shorter. The light ray's coming in like this. It bends toward the medium with the larger index of refraction. Now, if you trace that light ray back, you'll see that that light ray appears, that tree appears to be coming from, here. It looks like it's in a slightly different place. Okay, now when you have something called the critical angle, that's when total internal reflection happens. So a light ray that comes from just above the surface, like something standing on the shore, maybe a person on the side of the water here. It comes in and it bends. When it goes down here, that light ray is the last one that you are going to see. Because another light ray can't come from the surface. If you trace that one back, that shore looks like it's coming from, say, somewhere on this line. It doesn't look like it's coming from the shore. You're not looking towards the way over here to see it. You're looking straight up at the edge of your circle of vision. Now, a light ray coming from the side of the pool is totally internally reflected like this, and it comes to your eye in that way. So let's trace that one back. Okay, you can see that your eye thinks that that light ray came from here. So to you, it looks like everything from the outside world happens in this radius, and the rest of it looks like the side of the pool. All right, I've cleaned up the diagram and written the constraint for total internal reflection. So this is Snell's law that I've written over here. And it's for this light ray that was pen highlighted in green. So the incoming angle is basically 90 degrees. That's the incoming light ray. And the light ray continues, it bends in this direction at some critical angle, which corresponds to total internal reflection. I've got the index of refraction of air out here, that's 1. The index of refraction of water is 1.33. And so I can use this equation to find the critical angle, theta sub c, how I've labeled it. And notice that this is in geometry, this is alternate interior angles here. I've got one here and the same angle right here. So I can use this equation, Snell's law, for the case of total internal reflection to find the critical angle. All right, the sine of 90 degrees is 1, and so when I solve this equation for the critical angle, I get about 49 degrees for that angle. And so now I can do a trigonometry problem. Notice that I'm going to apply it to this triangle that I've highlighted in blue here. I'm going to apply a trigonometry problem and solve for the depth, because the side length that I've labeled y there is the variable that I'm looking for. All right, I have applied this trigonometry. R over y is equal to the tangent of the critical angle, and solved that equation for the depth y. And when I plug in the things that I know, I get that you are 1.7 meters deep in the pool. And that's how you use total internal reflection to solve this problem.